In this video, we're going to talk about the central limit theorem, the normal curve, and finding the probability of a sample average. So when looking at different sampling distributions in the central limit theorem, so when you graph population data, it can result in various shape distributions. So you can end up with a graph that looks like the one in the first column that looks almost normally distributed. Or you can look at the one in the second one that's kind of random values at the different levels. Or one like the third is almost inverse, it's almost U-shaped. And if you take a sample size of 30 from any of the populations above, so pick one of them, and then calculate the sample average, and then you repeat that many times over, you would have a whole list of sample averages. The central limit theorem states that the graph of a sample average, so if you take all those sample averages that you figured out, it is going to be approximately normally distributed regardless of the shape of the original distribution. So if we were to look at an example of that one, let's go ahead and say we have the GPA of current business students. And again, this is hypothetical data, so it's similar to what we looked at in the last video. So we have the GPA of current business students, and if we were to graph that, the histogram would show that it is certainly not normally distributed. If anything, it is skewed to the left. It looks more like the left tail. Everything is bunched up on that right-hand side, so that one is skewed left. When, if we were to go ahead and say, all right, well, let's go ahead and take our data, so the GPA of current business students, and let's take a sample of size 30. So I used the data and the data analysis and did a sample size of 30. And when I did that, I found that my sample average is 2.66. Well, my population average, using everything in the first column A, is 2.80. So my sample error in this one is going to be 2.66 minus 2.80. So we're going to have an error of about 0.14. So in our second sample of 30, we end up with a 2.74. So we have a sample error of 0.06. And if we keep doing that, you'll notice that a few times our population average is a 2.80. Well, on our fifth sample, we had a 2.80, but and on our seventh one or eighth one we did, but the majority of them are kind of randomly placed all around the outside of this. So if we go ahead, I'm going to go back to my first one over here, and if we take, let's say in this case, only 100 samples. I would probably have done more if it wouldn't have taken more time, but if we take 100 different samples, so we went out here, we took a sample size of 30, we found the average for our sample size of 30, 100 different times, and if we go ahead and graph that, lo and behold, it looks fairly normally distributed. So had we done more than 100 samples, we would have found that. So what this basically means is that we're going to go ahead and look at something that's normally distributed. So how does that relate to what we talked about in the last video? So the important points that we had in the last video, or on the last series of videos, is that when you graph the normal distribution, your mean is in the middle, and then you go out one standard deviation for every mark that you go over. Well, in this case, because we're not graphing the mean and a standard deviation, we're graphing the mean of the averages. So the mean of the averages, the mean in this case, the mean of our averages is going to equal the mean of our population. So we have our middle bar. The mean of our or the standard deviation, of our averages is going to equal the standard deviation of the population divided by the square root of n, where n is our sample size. So instead of going out 3 standard deviations and just having sigma noted here, we're going to use sigma divided by the square root of n, and 2 times sigma divided by the square root of n. So we just went out 3 standard deviations in terms of our x bar, so sigma divided by the square root of n. Another important point when we do this is the larger the sample size, the more it resembles a normal distribution. So a sample size of 30 is usually considered the minimum requirement. Some say 25, it all depends on where you want to go with it. So what we're going to do with this is we can use this to convert between sample average and probability and vice versa. So in the prior chapter, what we had done is we were taking a single random sample of a value, an x, and converting it to a percentage, or taking a percentage and converting it to a x value. What we're going to be doing in this new chapter is we're going to, instead of z being x minus mu divided by sigma, z is now going to be x bar minus mu divided by the standard deviation divided by the square root of n. So if we're going to use our equations in Excel to help us do this, we can convert from x bar to percentage and percentage to x bar just like we did in the last chapter. Only we're going to change one thing, or two things per se, in the values that we're going to be entering. So our equation is going to be the same, so equals Norm.dist, r equals Norm.dist, so if we're going to take our x to percentage, and in this one we did x, the mean, the standard deviation, and 1. So let's look at our formula. X is now in our new one replaced by x bar. So wherever we had an x, we're going to go ahead and put in x bar, right? Our standard deviation was on the bottom. So wherever we had a standard deviation, we're now going to replace that with the standard deviation divided by the square root of our n, or our sample size. So look at our equation. So we had standard deviation here, so comma the standard deviation of the population divided by the square root of n, which is our sample size. So we're going to go ahead and use this formula. You could also do it the old-fashioned way where you convert x bar to z and then use the back of the book to go from z to percentage. You're welcome to do that, or you could use the formula. Same thing to go from percentage to x score, or percentage to x bar. So in the last chapter we learned how to go from percentage to x. And so when we did it by hand, we went change from percentage to z score z to x. When we did it in Excel, we went ahead and said, go ahead and put in the percentage in the left tail. So we used the equals norm.inv, percentage in the left tail, the mean, and the standard deviation. So wherever you see the standard deviation, we're now going to replace that by the standard deviation divided by the square root of n. So percentage to x bar. You can do the same thing like we did in the last one, or we can use the equation and go equals norm.inv, the percentage in the left tail, so that's the same. The mean is the same. And instead of standard deviation, we're going to say the standard deviation of the population divided by the square root of n. So let's go ahead and see an example on that one, or a few examples. So we learned that the GPA of our current business students, that they had a mean, a population mean, or mu, of 2.8. We also learned that the population standard deviation was a 0.78. We want to know what's the probability that a random sample of 30 students are going to result in a sample average less than a 2.7. So let's go ahead and use Paint to go ahead and at least graph this to get a picture of where we're going with it. So if we say that our population mean is in the middle, so that's going to be a 2.8. And if we do how we were doing it from last chapter, so we were saying that, okay, so that value is going to be there. We want to know what's the probability that a random sample of 30 students will result that the sample average will be less than a 2.7. So our 2.7 is going to be somewhere in here, and I want less than a 2.7. So what are we going to do on this one? Well, we know that Excel returns the value in the left tail. So let's go ahead and use our equals Norm.dist function. So let's go ahead and equals Norm.dist. So our x value in this one is going to be our x bar. So this is going to be our x bar. We're going to do our mean. Our standard deviation in this one, remember we're doing the x bar in here. So this is going to be divided by the square root of n, comma 1. So let's go ahead and I'm going to leave that equation there for you to see it. So it's going to be equals Norm.dist of x bar, so we have 2.7. Our population mean is a 2.8. Our standard deviation in this case is 0.78 divided by the square root of our sample size, which is 30, comma 1. So it's going to return 24%. So let's go ahead and look at that. So this says that there is a 24.13% chance that we're going to find a sample average less than a 2.7. So let's go ahead and write that. There is a 24% chance that we will find a sample average less than 2.7. And we could, so given a sample size of 30. So we probably could have started that with a sample size of 30. There is a 24% chance that we will find a sample average less than 2.7. So the average GPA. Let's go ahead and do another one like that. So what's the probability that a random sample will be between a 2.5 and a 3.5? Let's go ahead and clear this. So I'm going to go ahead and do new and get a new one up there. So if this is 2.8, so we want 2.8 in the middle, our sample average, that's our population mean right here. And we're trying to see what's the probability that we're going to be between a 2.5 and a 3.5. So we want to go between a 2.5 and a 3.5. So the area we're trying to find is that one. So in Excel, we're going to find, I'm going to change that to black, we're going to find the probability that a 3.5 will occur, and we're going to subtract the probability of a 2.5. That will give us this range in through here. So we're going to take those two values, we're going to find them, and then we're going to subtract the two of them. So let's go ahead and do that. So just like we did in the one above it, equals Norm.dist. Our x in this case, we're dealing with x bar, so it's going to be 3.5. Our mean is 2.8. Our standard deviation, remember, because we're dealing with x bar, is going to be then 0.78 divided by the square root of 30. So the square root of 30, comma 1. So there's a 100% chance that that would happen. So let's go ahead and find out what happens with a 2.5. So equals Norm.dist with a x bar of a 2.5, a mean of a 2.8, a standard deviation of a 0.78. In this case, because we're dealing with x bar, we have to do divided by the square root of n, which n in this case is 30, comma 1. And if we subtract the two of those, we find that there's a 98% chance that a random sample of size 30 students, will give us an average between 2.5 and 3.5. So there, with a sample size of 30, there is a 98.2% chance the sample average GPA will be between 2.5 and 3.5. Let's go ahead and do one more sample and do it the other direction. So we're going to go ahead and take our percentage value and create it back. So our question here is home. All right, so I'm going to go ahead, given a sample of size 30, what's the sample average associated with a top 10% in there? So let's go ahead and once again graph it. So I'm going to go ahead and say new. All right, so let's go ahead and graph that. With a sample size of 30, the sample average. So again, what we know about this is a 2.8. We know that we want to find where the number that's associated, the sample average. So the sample average associated with the top 10%. So let's go ahead and graph that. So we know that's 10%. So this one's going to be 0.100. Well, when we enter the formula in, it's always going to be the amount in the left tail, so the amount in the left-hand side of the line there. So if that's 0.1, this is going to be, oops, let's go there. This is going to be 1 minus 0.1, so that's going to be 0.9. So if 10% falls on the right, 90% is going to fall on the left. So let's go ahead and find out what that value is going to be. So equals norm.inb. Our probability in this case is 90%. Our mean is going to be 2.8. It's our population mean, divided by the standard deviation. So in this case, because we're dealing with the x-bar again, given a sample size of 30, we're dealing with the sample average. And that's what the question asks, what's the sample average associated with the top 10%? We want the standard deviation by the square root of n. So this is going to be 0.78 divided by the square root of 30, and that would be the end of our equation. So the value associated with that is a 2.98. So if we were to go back up here and put that value in, we have now found that the value here is a 2.98. So that means there is a 10% chance that the sample average will be more than 2.98. So let's add what we need to on the front of it. Given a sample size of 30, there is a 10% chance that the sample average will be more than 2.98. So if we did a sample and we found that our average came to a 3.2, we'd know that we would be in that top 10%, or actually it's going to be higher than that at that value. But we know that we only have a 10% chance of getting anywhere in that 2.98 or higher. So that answers those three questions. Keep in mind that the last chapter, when we looked at it, what we looked at is what is the probability a single student will have an average less than a 2.7. So when we did that one, let me move this over just a little bit, we went ahead and used the Norm.dist function, and so our x1 in this was a 2.7, our mean was a 2.8, our standard deviation, because we're dealing with a single observation or a single student, is just 0.78. You could have said divided by the square root of 1, but that's going to get you the same thing. So that's going to be comma 1. So interestingly enough, there's a 45% chance that the student will have an average, a single student will have an average less than a 2.7, but with a sample size of 30, their average is going to be a 24%. It's going to take a little bit to get used to this, but we'll move forward with it and learn more about it in some future videos and how to use it.